I can find a magic pen, there it is. And if I could find the things to write with. Oh, wrong button. Wrong screen, I guess. There we go. There they are. Okay, so 8, 7, number 2 should look something like integral, at least mine, was 9 to 17, 7 of 1 over x minus 9 to the power 1/9 dx. And so the problem with this thing right here is at x equals 9, it's undefined, right? So that's trouble. So we have to redo this by taking the limit as x approaches 9. And since we're going from 9 to 17, I could make a note that we're approaching 9 from the left side. And I don't want that to be an x. What's that? Oh, yes, right side. Thank you. I don't know my right from my left. From A to 17, and be careful, my A's and 9s look a lot alike, which is sometimes troublesome. X minus 9 to the power 1/9 dx. So I'm just going to hold off on the limit for now and just consider the antiderivative here. Do we have an antiderivative for x minus 9 to the negative 1/9? So that's kind of like u to the negative 1/9. Yeah, so we increase the power by 1, so that would give us 8/9, yep. And then du, well, that would be the derivative of that, which is just 1, so there's no big loss there. Okay, so I'm pretty sure the antiderivative here is x minus 9 to the power 8/9 divided by 8/9. Or if you like, you could multiply by the reciprocal, 9/8. And that's from A to 17. Yeah, we'll flip that over in a sec. And then eventually we'll take the limit of this, so we'll come back to that. So here, let's pull out that 9/8, and we plug in our 17. So 17 minus 9 is what, 8 on a good day? So we have 8 to the power 8/9 minus a minus 9 to the power, and that is a 9, not an a, 8/9. There we go. And so now we have something that we can take the limit of. So let's switch back to black. So taking the limit as a heads toward 9 on the right side, let's see, what do we get? Well, I guess I need to recopy that to be accurate with my notation. What do you think? Do we safely let that go away there? The closer we get to 9, this sucker right here is, let's see, we're always a little bit bigger than 9, so it's going to be a positive number that's getting closer and closer to 0. And 0 to the power 8/9 on any given day is usually 0. Yeah, okay, so it looks like we do have a limit here. It appears to be 9/8, and we can probably clean that up a little bit, times 8 to the 8/9. So cleaning that up, I could view this as 8 to the 1st, and applying the power rule for division, or the exponent rule for division, that gives me 8/9 minus 1, which is what, negative 1/9? So ultimately, it looks like, I'll write it up here, we get 9 over 8 to the 1/9. Positive exponent in the bottom. Do they give us any guidelines on how to type it? Type an exact answer using radicals as needed. I don't think we need a radical. I've always been fond of fractional exponents. Let's see, what does the answer key say? Is that the way they wanted it? Oh, they're so naughty. I don't like that. Oh yeah, that's the way they say here. I wonder if they'll take it. They won't take it with the fractional power? Oh, that's rude. All right, fine. So the book or the online homework wants the 9th root of 8 in the denominator. Oh well, that wasn't too bad. All right, let's try another one. Number 12 apparently is fun, and I got to reorient my board. It is misbehaving again. Pretty much, yeah. That's one reason I like my bicycle. It's relatively low tech. It has like no electronic components unless I hook up one of those little trackers to it. All right, ooh, this is gonna be a fun one. We've got the integral from -infinity to infinity of 1 over the square root of x squared plus 8 with respect to x. And does it converge or diverge? And the book goes over some ways to test things like this. So let's take a look at the tests they have in there. Math 252, chapter 8, section 7. And make you wider. Okay, so that's not what we want. Yeah, so there's a p functions. Let's make that a little bit bigger, which this is kind of sort of related to. Like the function 1 over x we took a look at, when we tried to integrate that to the right forever, we found it diverged. But 1 over x squared, it converged. And so they kind of have a rule here that they develop, that the improper interval converges if p is greater than 1, and it diverges if p is less than 1, if you have something of that form right there. So then the question is ours in that form? And because of that plus, it's not really, but we could do a substitution to make it look like it. Maybe. Let's see. I don't remember. Do they have any other rules? Type 2s we just looked at. And then computer algebra system. Test for convergence and divergence is not very helpful. Ooh, the limit comparison test is, that's a good one. Okay, so I think we can use that. So what we'll take a look at is compare this to, my pen's not working again. Let's hope this one works. There we go. So we're going to consider what's called the limit comparison test. And what it says is, if you can compare this to a function that's simpler but similar, there we go. And you take the limit of the similar functions in a quotient as x goes to infinity, if that limit is constant, right, you get a real number, then either they both converge together or both diverge together. Okay, so the plus 8 is kind of a pain here. So a simpler version would be to say, well, what if we had the integral of 1 over the square root of x squared? That's a simpler version of the one we have here. That can be simplified, right? That's the integral of 1 over x with respect to x. And what does this do right here? Does it converge or diverge? Yeah, for 1 infinity, it diverges. For 2, it's definitely going to diverge. Yeah, so this diverges. So now if I can show that the limit of their quotient is constant, then I can show that this black one has to diverge too. Okay, because think about it, for big X, does a +8 matter? Not really. So that's kind of the theory behind this here, in an intuitive sense. So let's take a look at the limit as x goes to 0, infinity, excuse me. And you can write the functions in either direction. I'm going to write the square root function on the top and put the square root of x squared, or just x, on the bottom. Okay, so that's the function I'm comparing it to. Could you flip them? Yep, it's up to you. I think this one's going to be easier. So often what I do is if I'm not sure what to do, I just guess. And then if it doesn't work out, then I flip them and try again. So what can we do with this? Well, they're both positive, right? So that means I can combine the square roots into 1. So I have a big square root of x squared plus 8 over x squared. Anything nice happen here? Yeah. X squared divides both of these, so this then becomes the limit as x goes to infinity of the square root of 1 plus 8 over x squared. Now, thinking way back to calculus, we've got some rules for limits that say you can take the limit, you can bring the limit into a function like the square root if the limit exists. Well, we have to check to see if the limit exists. You can also take the limit across a sum, wrong magic pen, if each limit exists. So what's the limit of 1 as x goes to infinity? Well, it's 1, yeah, so that's cool. And what's the limit of 8 over x squared as x goes to infinity? It's 0. So both limits do exist. I do have the right to take the limit in there. So this must be the square root of 1 plus 0, which is 1. So what that means is they both grow at the same rate, is what that means for big X. So they have the same growth rate for big X. That means they behave the same. So that implies that our integral from negative infinity to infinity of 1 over the square root of x squared plus 8 has to diverge. So that's what they meant by use a test. What do you think diverge means here? Because diverge can mean a couple of different things. It could mean it doesn't settle down, or it grows without bounds. Okay, so doesn't settle down means it bounces around between different answers. Like a sine function bounces around, right? So in this case, the diverge means it's going to grow without bound, which is what we discovered when we did this integral the other day. It kept getting bigger and bigger and bigger and bigger and bigger as we kept moving to the right. That was the other one, yeah, that the paint thing was the other one. So growth without bound is what this divergence means. Because another kind of divergence would be, what's the limit as x goes to infinity of, say, the sine of x? Well, the sine of x is always between 1 and -1, but it's always a different number between 1 and -1 depending on which x value you pick. So this diverges for a different reason than the other one, because there's no fixed number. It's somewhere between -1 and 1. Whatever x value you stop at, it's some number between -1 and 1, right? So that's a different kind of divergence than growing without bound. Is there another way we could do this problem right here besides that limit comparison test? You could do an integral substitution, yeah. So let's see if we can do that. Do we remember seeing this in any of our previous integral tables? It does, yeah. Yeah. So if I let a equal the square root of 8, then this is a u squared plus a squared in the denominator, and there's probably an antiderivative. So if we go over to our resources page, or Wolfram alpha, let's go to our resources page. Sometimes Wolfram alpha takes all the fun out of it for me. Makes it too easy. Let's see, I want integral formulas. And then scrolling down. Samantha, we need to control that addiction.
Who's addicted to what?
Darren wants to know who's addicted to what. We're all addicted to technology, Darren. We're slaves to it.
Oh, well, that's just a given.
Yeah, Darren says
We've
that's
been
given.
addicted to technology since the BCs.
Yeah.
Back then it was
forget. Oh, there it is right there. And does this function look familiar here? The natural log of u plus the square root of a squared plus u squared? Yeah, I'm pretty sure that's the inverse arc cinch. Yeah. So let's think about ours for a minute. So we have the natural log of u plus square root of a squared plus u squared. So that means we do have an antiderivative here. Oops, wrong magic pen. New page. So we're going to go from a to b because we legally can't. Infinity isn't a number. 1 over the square root of x squared. And I mentioned that if we say a is the square root of 8 and we square it, right, that gives us our 8 back. And so the formula said take the natural log of u, which in this case is x, plus this same square root right there, square root of x squared. I'm going to call it 8 this time, plus 8. That's my antiderivative right there from a to b. And what's going to happen as, say, b gets large here? It's going to keep on growing positively. The other way, we keep on growing negatively. Is that true? Do we grow negatively the other way? No, this thing is always positive. Yeah, this thing is always positive. And so it's going to go to infinity in both directions. So this one's going to head us to infinity, and that one's going to head us to infinity too, because my integrand is always positive. This one right here, I think it's a bell-shaped curve. Let's take a look. That's a good question. Oh, what does the natural log look like? It is, I think it looks a lot like the regular natural log, but it heads out in 2 directions. Let's ask Jude. I want to graph both functions actually. So let's look at 1 over the sqrt of x squared plus 8. There we go. And usually if I just type a function, they'll give me a graph of it. Yeah, so this is a bell-shaped curve with asymptotes heading out along the x-axis. So that's the function we're integrating, but it looks like it doesn't drop down fast enough to have the area be minuscule at the ends. It's significant. And then our natural log function of x plus that square root squared plus 8, another parenthesis, right? It looks linear, but it's not linear. Let's see, does it give us another? Yeah, so here we can see it curving out on the sides there. And can we change the boundaries on that? There was a way. Nope. Oh, it looks like we have to go pro if we want to see more of the graph. So we could ask Georgia, but what we're going to find, it's going to head out in each direction and just keep growing. Okay. What's up, Darren?
Integral calculator.
The integral calculator. Oh, the integral calculator zooms, doesn't it? Okay, fine. We'll use the integral calculator. Darren is whispering in my ear. If you want to hear what he had to say, you can go listen to the video later. x squared. I don't know, sometimes the voices are right. Plus 8. Okay, ooh, cool. Yeah, so it's showing us quite a bit. And let's see, if I use my wheel, I can zoom out. And it's going to grow shallow, but it's going to keep growing forever and ever and ever. I believe that is an area function. Notice it's the same shape as the red one, but shifted. They must have some definition of it here somewhere. Control F, F star. No, they don't have a definition of it here. Huh. I'll check out their documentation later. But my guess is it's just a different antiderivative because it has the same shape. Remember, any two antiderivatives can be shifted up or down from one another. That's my guess. All right. That was fun. Oh, I was going to double check that my belief was that was the arc cinch. So if we double check, oh, you looked it up? The inverse arc cinch. Oh, the integral calculator showed the inverse arc cinch here. Oh yeah, they show the alternate version. Provided we use the constant 2 to the negative, 2 to the 3 halves in the denominator. Cool. All right, any other questions you guys want to go over? No? Okay. I have a brief commercial interruption though. Let's see. MIT, Massachusetts Institute of Technology, try saying that 5 times fast, has a lot of free stuff online that's cool. So their calculus course is available free online. They also have a differential equations course. And a couple people asked if we could offer differential equations next term or this summer. And there's a good chance. Differential, type that right? I don't think so. Equation. Oh, I didn't type it right. Differential equations. Will they show it to me? Yeah, there it is. So I'll post a link to this. So if you want to see what a differential equations course is like, I usually model my differential equations course after MIT's. We can't cover everything they do because they're a semester course. So we usually don't get to much of their unit 4, but we usually cover their 1, 2, and most of unit 3. And I have a free textbook that we can use along with it, which is kind of nice. So it's a low cost course. Yeah. What is that thing right there? That is a slope field for solving a system of differential equations. So an example of something that might look like that, I don't know if anyone's noticed there's rabbits that live on campus. Okay, we also have critters that eat rabbits, like coyotes and foxes around here. So if the rabbit population gets really big, that's going to attract predators. So the bigger the rabbit population, the more predators it's going to attract. Well, the more predators come, the more rabbits that get eaten, and the rabbit population drops. And so the rabbit population and, say, the fox population are interrelated. As one changes, the other has to change too, and they form these crazy cycles. And sometimes the cycles they make might look something like that there. So toward the end of the course, on a good quarter, we might have time to look at systems where we can see, like how rabbits and foxes interact, which is kind of exciting, I always thought. So I'll post a link to this for anyone that wants to check it out in our resources. And then we'll take a problem from the practice final.
Do you know how to get to the instructor evaluation, course evaluation?
You know, I should know how to get to the instructor course evaluations. I will try in just a sec. Let's see, I want to go back a level.
It's supposed to just pop up when you
when you log into Canvas, or into a course, it should just pop up.
But it hasn't.
Okay, differential. Okay.
I had it pop up for my health class, but not my bio.
Oh, okay. I can ask about that. Okay, so I posted a link to MIT's course, and then I can share later or answer questions for anyone that has them later. All right, so let's see. Let's go into one of my alternate realities. No. New incognito window. Let's go to Google. No, where do I want to go?
This is very
Canvas.
scary right now.
Uh,
Going into incognito mode, looking at your
Yeah.
history.
Okay, let's see. One of my alternate personalities is Gary.Parker at gmail.com. Password. Oh, that one. If I go in to Canvas as a student, it should say, oh, I've never accepted my invitation to join this class. Oh, I bet my grade's not very good. Let's accept. And then when I get to Calc 2, it should say, hey, fill out a survey, and it doesn't. Oh, if I go to my courses, winter, I'm also in general biology. Cool. And, oh, that one pops up, but mine doesn't. Okay, I will ask the people in charge.
I do not envy that student.
Course
All the
eval. Ooh. The student that's in these courses? Is that what you're saying, Darren?
Yeah, I do not envy their course load.
Yeah, that's because people ask me to test stuff, so I'm involved in a lot of different courses. Like my picture, isn't that cute? That's my dog. Okay, let's take a look at the sample exam. What looks cute here? 2. Oh yeah, that's a great one. All right, so we want the derivative of the integral from 0 to x of 1 over t dt. Love that one. So the derivative with respect to x of the integral from 0 to x of 1 over t with respect to t. That is a direct application of the fundamental theorem of calculus part 1, which says that integrals and derivatives cancel each other with one catch. What's the catch?
They differ by a constant.
Well, you gotta have the dummy variable, but the chain rule says you have to multiply by the derivative of any variable boundaries. So since I have a variable boundary x at the top, I have to multiply by the derivative of x with respect to x, which in this case is 1, no big whoop. So that's okay. So this is just 1 over x. So if that's just an x at the top, and it doesn't matter what the bottom boundary is. Okay. Oh gosh, I lied. Oh no. Okay, so this is a trick question. I don't know if I did this on purpose or not. I don't think I did. I think this is an accidental trick question. Okay, so in general, this is amusing, only for a math geek though. The integral from some value a to x of little f of x, or f of t, sorry, dt, the fundamental theorem says that as long as f is differentiable, then this is f of x. Doesn't matter what that bottom boundary is, as long as it's differentiable. So that's the catch. F is differentiable. What does it mean to be differentiable? Differentiable. Oh gosh, that's going to hell, isn't it? Differentiable. Okay, there we go. To be differentiable, that means the derivative has to exist at that x value. Question, is the derivative going to exist when x is 0 here? Okay, so if we do this by the slow method, and the slow method would be to first consider the integral from 0 to x of 1 over t dt, right? The fundamental theorem allows us to skip this step if f is differentiable. And the problem here is 1 over 0 is undefined. Oh, I put an x there. That should be a t, yeah. That's undefined. So this is an improper integral. So I have to rewrite this as the limit as a goes to 0 of the integral from a to x of 1 over t dt. Okay, what's an antiderivative for 1 over t? Natural logarithm, yeah. So this would be equal to the limit as a goes to 0 of our antiderivative natural log of the absolute value of t as we go from a to x. And what's the value of the natural log of 0? Nope. So here's the way to think about it. Let's see, new page. The natural log of 0 is equal to what? Means e to what power is equal to 0? Not 1.
You say it's not 0, so.
Not 0.
Well,
Yeah.
it's-
There's no, this is impossible. This is not possible. If you think about the exponential function, right, it looks like this here. It grows that way and it's asymptotic this way. And it's always greater than 0. So there is no answer here. No answer. If you consider flipping x with y, you get the inverse function, which is the natural log, and that looks like this. And it's asymptotic. So this is asymptotic toward the x-axis, this is asymptotic toward the y-axis. So it drops forever. So you might argue that the limit is negative infinity, which it is. It does decrease without bound, but negative infinity isn't an answer. So the lower end point here, this decreases without bound. It diverges.
Did you realize this when you were writing the test?
No, I think I meant to put a 1 here at the bottom and I slipped and put a 0, I think is what happened. Yeah, I meant it to be an easy question. I didn't mean it to be a hard one. So if I put anything but 0 there, any positive number but 0, sorry, then this is going to be equal to 1 over x. Okay, but once I threw 0 in there, I made it way more complicated. So my apologies. So if that 0 stays there, then this is a divergent situation, which is a problem. So what I meant to have was something like the derivative with respect to x of the integral from 1 to x of 1 over t dt. This is equal to 1 over x. So let's do a slightly harder but easier version. What is the derivative with respect to x of the integral of from negative 3 pi over 17 to x, x squared, oh yeah, of the sine of t dt? Does the constant lower boundary really matter? Answer is no, because I'm taking the derivative. And so the fundamental theorem of calculus says take the original function, sine, plug in your upper endpoint, x squared, but then the chain rule pipes in and says, hey, my turn, take the derivative of that upper function, which is 2x. So that would be the result here. And that's according to the fundamental theorem of calculus part 1. That's a weird abbreviation. I've never done that before. Secret code. All right, let's try. Part 2 says you can use any antiderivative to evaluate. So fundamental theorem part 2 says if capital F prime of x equals little f of x, then the integral from a to b of little f of x dx has to be equal to capital F of b minus capital F of a, capital F. And this is the fundamental theorem of calculus, part 2. It lets us use any antiderivative of the function to evaluate at the endpoints and skip the whole Riemann sum stuff in between. All right, let's see, what else looks cute? O looks cute. J, E, A, B, C, D, E, F. Oh, that's a good one. Would F just be 1? Answer is no, it wouldn't. Yeah, that is another one of those trick questions. Seeing if you're paying attention. That one I did on purpose. So if we wanted to take the integral of the sine of x over x, what tools do we have at our disposal? Well, any trig identity isn't going to help because of that x in the bottom. And any substitution with x isn't going to help with the sine. Any substitution with the sine is not going to help with x. So if I tried to do trigonometric substitution for example, I would end up with sines and like inverse sines all in the same place, which is not a pleasant experience. So if we go to some place like Wolfram alpha in desperation, or looking for inspiration, that's my other excuse, and I ask for the integral of the sine of x over x, it's going to say, oh yeah, that is the SI function, capital SI. There's a lowercase si, which is a different function, which is kind of like the ERF function. It's just this special function that only exists as an integral. Okay. So my advice to you is when you get a problem like this, just think like, okay, what tricks do I have up my sleeve that might try? Give something a shot. If it feels like you're heading down some crazy rabbit hole, then go to some place like the integral calculator or Wolfram alpha and say, what advice do you give me? And then try implementing their advice. And so here, what's that? Since here they say it's the SI function, we're like, oh, we don't have any tools, but something like Wolfram alpha or Simpson's rule, if we wanted to come, like if we were going from 0 to 2, for example. So hang on, Darren. Stanton had a question.
So would we have these tools available to us during the final or?
Yes and no. So the first part of the final is going to be a short page of integrals that you can't use any kind of calculator on. And then the second part is you can use whatever you want on, but I want to see work. Okay. Okay, Darren. What's up?
I was pretty much asking the same thing.
Same question. Yeah, so for example, your test will have like maybe 5 or 6 like this that you can do without something like Wolfram alpha. And so I'm going to ask you to just do them without any kind of calculator. Just find me antiderivatives. And then any question that involves calculations like definite integrals or crazy surface areas, then you can whip out any kind of tool you want. GeoGebra, Wolfram alpha, integral calculator, as long as you show me some relevant work to go with it. Yep.
And so would the final be in here? Would we have like a computer lab?
Yeah, if you need a computer, you can jump into the lab next door. Yep. Or whip out your smartphone. Yep. The only thing you can't do is ask another human being to do it for you. But feel free to ask any of these online robots to do stuff for you. Okay, should we try? But you can't ask a human? Is that that's like morally unsound, maybe? Yeah, and there are websites that human beings respond to. Like they have like a robot that goes first. If it recognizes the question, it sends you to a page. And if it doesn't recognize the question, then it sends you to a human. Like my stepfather used to do that for Google. If a Google search didn't come up with something relevant, they could say, ask one of our specialists, and Google would send it to like my stepfather. But the way that works is they have a whole group of people like my stepfather, and it's whoever gets it first and sends the answer out gets paid. So you could, like, if you're not fast enough, you could do a ton of work and never get paid, right? So he was fast enough half the time, so he quit that job after a while. He said it was not pleasant. All right, let's try another one. We got enough time for one more. Shall we do like an area, Riemann sum, a volume? Riemann sum, okay. So here I have the Riemann sum of x squared. Should we do that one or something more complicated?
That's good.
That one's good, okay. So new page, we want, uh-oh, oh no.
Here, we're pen's out, Sally.
Oh, there we go, pen's back. All right, so we want the integral from 0 to 1 of x squared dx, and we want to do this with a Riemann sum with n subintervals. If I read that right, subintervals, there we go. I don't know what I'd do if it wasn't for phonics. I wouldn't be able to spell anything. Okay, so where'd you go? Oh, no, I'm doing the wrong one. Oh, there's two different versions. Okay, there's an upper sum on x squared from 0 to 1 with 7 rectangles, and there's a generic Riemann sum with n subintervals. Which one do you want to do, 7 or n? Oh, that's almost unanimous. Okay, so we have n here. So the first thing we have to do is find the width of our interval. So that's 1 minus 0 or 1. So delta x is going to be the width of the interval 1 divided by how many subintervals n. My x values, x sub k, they start at 0, and then I'm going to add on k multiples of 1 over n. So I'm going for right-hand endpoints. So right endpoints. Notice the previous problem said upper sum. So then you'd have to say, oh, what's bigger, the right-hand endpoint or the left-hand endpoint? Do they switch? So upper sums are way more complicated. I'm just going for right-hand endpoints. So my x sub k values simplify to just k over n. Once I have that, I can set up my Riemann sum. So that's going to be the sum as k goes from 1 to n of my function x squared evaluated at my little x sub k's. So k over n. And it's always a good idea to draw a picture, which I skipped, which is bad of me. So let's put a little picture in here. And x squared, if I zoom out a little, if I say that's 1/2 and that's 1, that's 1/2 and that's 1. I know I have a point at 0, 0 and 1, 1, and then 1/2 is 1/4. So it looks something like this. So this is my function y and x, and I'm splitting this up into a bunch of little pieces. And I'm grabbing those rectangles. The width of each of these rectangles, that's my delta x. That width right there, that's just 1 over n. And so, again, as I move along here, right, starting at 0, I keep adding 1 over n, and then add another 1 over n, then add another 1 over n, then add another 1 over n, right? And so that's where I got this formula right here from. So at any point, if I want to get the height of this rectangle, and that's a right-hand endpoint, so it should be way up there, I just plug in the particular x value I have, okay? So in this case, it's the kth interval, so it's k over n. Okay, what can we do with this sucker right here? Oh, I forgot something. That's the height of the rectangle. What's the width of the rectangle? 1 over n. Now, got to put that in there, right? Because this has to be the sum of the areas, right? And an area is the height times the width. Okay, so cleaning that up a little bit, I'm going to rewrite it. K equals 1 to n of k squared over n squared times n over n cubed. Now, what's the variable here in my sum? It is k. Yeah, n is fixed. So in the previous example, n was going to be 7. Maybe n could be 10 or 100 or 1,000. So once we pick an n, we're stuck with it. But k is the variable here. That means the n cubed is a constant. It can come out of the sum. So I can rewrite this again as 1 over n cubed times the sum as k goes from 1 to n of k squared. And we have a formula for that. Let's see, do I remember it? I think, let me try, I'm going to guess at it. I think it is n if you're going to n for the squares, I think it's n times n plus 1 times 2n plus 1 over 6. I still have that 1 over n cubed out front. I'm going to look that up because I'm not quite sure if that's true. Okay. Do you like chocolate? I'll bet you a chocolate bar. All right, Stan disagrees with me, so we're going to look it up. You don't have to accept that wager, by the way. Okay. Oh, cool. I don't have any chocolate on me, but hopefully I owe you some chocolate. Let's see. This was in chapter 5. Yours is what? French chocolate? Oh. Okay. It's not there. Oh, there it is. Okay. Oh gosh, get back here. Come here. Okay. Oh, I was right. Yeah. So the cube, the linear one, if it was just k, it would be n times n plus 1 over 2. The squares is this crazy thing, and the cubes, interestingly, is the square of the sum of the first k integers, which is kind of crazy. And I remember years ago, I figured out like, what about k to the 4th and k to the 5th? I think I was on a plane ride and there was no good movie. And so I think, what's that?
Swimming.
Yeah. You do math while you're swimming? Yeah, when I do long bike rides, I do math. I've solved some really good problems bike riding. Okay, so it is this one right here. So Stanton owes me a chocolate bar. Cool. Okay, Tuesday's cool. All right, so again, just summarizing what I have here, the sum of the first k squares is this right here. I still have the 1 over n cubed out front. Now this makes me happy because if I multiply out the numerator, I have an n cubed in the top, and they will balance each other when I take the limit. So the next step would be to take the limit of this sucker. So what is the limit as n goes to infinity of n times n plus 1 times 2n plus 1 all over 6n cubed if I put that together? Now, if you remember back from your limits of polynomials, all that matters is the leading coefficients if they're of the same degree. So what's the leading coefficient of the top? Well, that would be n times 2n. So in the top, the leading coefficient is 2n cubed. Bottom clearly is 6n cubed. And for big N, this is all that matters. The n cubes essentially divide out, leaving me a limit of 2/6 or 1/3. So what we did is we took a generic Riemann sum that says, hey, just go up to n, maybe n7, maybe it's 10. And then if we can simplify the sum, then we can try and take the limit. What if we couldn't simplify the sum? We can't take the limit. What if we simplify the sum, but we don't recognize it as anything we've ever taken the limit of before? Yeah, you might be able to, you might not. And so then you just have to say, okay, well, let's let n be 100 today and let a computer help us calculate it, right? Then we have to use something like an actual Riemann sum or the trapezoidal rule or the Simpson's rule, okay? So for anything that's not a polynomial, we pretty much can't do this. It's just, it doesn't work. The best you can do is keep letting n be a bigger number and see if you recognize the number it's leading to. Right? It's kind of crazy. Yeah. So we're out of time for fun today. I'm gonna go do yoga. You guys have a fantastic weekend. Maybe I'll see you tomorrow. I'm gonna do a review session tomorrow, and then we got another review session Monday, and then the exam is officially on Tuesday. For those of you interested in differential equations, I now have a somewhat official list of people that want to do it. I'm going to send the note to my boss today and see what happens. So hopefully we'll have differential equations next term or this summer. Yeah, 2 in 1 term is tough. When I was a student, I went to the community college first and finished all my general electives, which meant when I transferred to the university, all I had to do was take classes in my major. Well, since my major was math, that means I took like 3 math classes a term, every term for 2 years. It was very exciting.
I don't think I could do that. I would
Yeah.
at least want to like.
I got cocky one term and I tried to take 4. Ooh, that was, don't recommend that. That was a mistake. Don't.
I mean, let's say like algebra 1.
Yeah, no. These were like, you know, calculus 3 and 4 and 5 and 6. Yeah.
Getting on 6 while you're